Okay, hi everybody. So this part of the question is the new bit. The part before, although there was quite a lot of aspects to take into account, there were a lot of weights, we have done this sort of thing before where we are working out the reactions based on forces and the distance away. In this next part, what we're going to do is we're going to consider what weight we would require so that the bar tips over. So we're looking at some new ideas here. Just a reminder, in the previous question, this mass was 20 kilograms and this one was 10. So it was a little bit lopsided before, but now what we're going to do is we're going to increase this mass even more. So much so that it's about to tip over. Everything else is going to stay constant. So the bar still weighs 20 kilograms or 20 kilograms. This mass over here is still 10 kilograms. We don't know this mass, so I'm going to write it as m times 9.8. So I don't know what it is in terms of kilograms. We'll leave it like that for now. Now, in terms of the setup in this question, there's still going to be a reaction force acting upwards here. But because the object is about to tip, it means that it's about to lose contact with this support over here. So the setup that's going to be, well, the thing that's different about my setup is that this reaction force is no longer present. It's just a reaction force of 0, or it's just not there at all. That's what we're dealing with. Okay. Distances are all the same. So this is still 0.1 meters. This is still 0.6 meters. And I don't know if I want to draw another arrow on. I'll try it. It'll be a bit wonky. Sorry, guys. There we go. And that distance there is still 1.3 meters. So we can piggyback from the previous part. We can use a lot of that information. Now, let's still consider moments from the same place. And we're keeping in mind here that there's no reaction force over here. So what have we got? Let's go over here with the numerical stuff first. So the moment from the bar itself, I'm going to pinch from the previous example. It's up here. That's going to be 0.6 times 20g. That was 117.6 Newton meters clockwise. This mass over here was 1.3 meters away times 10g, which was 127.4 Newton meters. That was clockwise as well. Cool. Now this bit, the distance is still the same, 0.1, but I do not know the mass anymore, so I'm just going to keep it in terms of m. And 0.1 times g, 0.1 times 9.8, I probably didn't need the calculator for that, let's be honest, is 0.98. Okay, cool. 0.98 m. There we go. Once again, we say these forces are going to be balanced. So let's set it up moments clockwise equals moments anti-clockwise. So we add up these values that I've got in green. And I write over here 0.98 m. These numbers added up to 245. And if I divide 245 by 0.98, I should get the value of m. And dividing by that number should increase it very slightly. I think it'll go up to about 250. It comes out as 250. Brilliant. There we go. So in order to tilt the bar, you'd need a mass of 250 kilograms. That seems like quite a lot, to be honest. So this is very much the weight training scenario if one arm is a little bit stronger than the other. I don't know, 250 kilos, man, that's a lot. Yeah, maybe you just don't do this. This probably don't seem like a good idea. All right, hopefully that's useful. See you in a bit.